Welcome, my friends! In this video, we will be expanding logarithms using the properties of logs. Predominantly, we will be using the power rule, log of a product, and log of a quotient properties. Let's get started. Consider log of y divided by x to the 8th power. We need to rewrite the log so that each log involves only one variable and does not have any exponents. We know from the log of a quotient rule that if the argument of a log contains a quotient, the log can be split up into two separate logs that are subtracted. This can be simplified to log of y minus log of x to the 8th power. Now we need to write this without exponents, so we can use the power rule for logs to rewrite this with the power out front, so that our final answer is log of y minus 8 times log of x. How about log of xy to the 4th? This time we can use the log of a product property to rewrite this as the sum of two logs. We have log of x plus log of y to the 4th. We can again use the power rule to bring the exponent of 4 out to the front, so that we have log of x plus 4 log of y, which is our final answer. Let's try some slightly more difficult problems. Consider log of x to the 5th power times the cube root of y squared z, which we want to rewrite with one variable per log without radicals or exponents. First, we know that the cube root is the same thing as the 1/3 power, so let's rewrite the radical as the 1/3 power. We have log of x to the 5th power times y squared z to the 1/3 power. Now we know by exponent rules we can distribute the 1/3 to the y and the z and multiply the exponents. We have log of x to the 5th power, y to the 2/3 power, z to the 1/3 power. Now we can use the log of a product property to split this into three separate logs that are all added together. We have log of x to the 5th power plus log of y to the 2/3 power plus log of z to the 1/3 power. Now we can use the power rule to bring each exponent out front so that we have 5 log x plus 2/3 log y plus 1/3 log z, which is our final answer. Let's try another one. We have log of z to the 3rd power divided by y square root of x to the 5th. We can do this in a few different orders, but maybe I'll start by splitting this into two logs using the log of a quotient property. We have log of z to the 3rd minus log of y times the square root of x to the 5th. On the second log, I know that the square root of anything is the same thing as the 1/2 power, so I can rewrite the problem with x to the 5th power raised to the 1/2 power. We can multiply the exponents to get x to the 5/2 power. Now we can separate the second log using the log of a product, but be careful. We need to use parentheses to indicate that both terms must be subtracted from log of z to the 3rd. We can distribute the negative sign so that we have log of z to the 3rd minus log of y minus log of x to the 5/2. Now we can use the power rule for logs to bring down each of the powers. We have 3 log of z minus log of y minus 5/2 log of x, which is our final answer. How about log of the square root of x plus 4 to the 5th power divided by x to the 5th power? Well, we know that the square root is the same as the 1/2 power, so we can rewrite the argument of the log as the 1/2 power. Then by the power rule for logs, we can pull the 1/2 out front. Then we can split the log into two logs using the log of a quotient rule, but we have to use parentheses to indicate that the 1/2 multiplies the whole log, so that we have 1/2 log of x plus 4 to the 5th power minus log of x to the 5th power. We can use the power rule to pull the exponents out front, so that we have 1/2 5 times the log of x plus 4 minus 5 times the log of x. There isn't really anything else we can do to simplify this. We could distribute the 1/2, but that isn't really necessary. This could be our final answer. Let's try log of 6 times x plus 5 squared divided by the cube root of x to the 4th power. First, I'll rewrite the denominator as raised to the 1/3 power instead of the cube root. Then we can multiply the exponents to get x to the 4/3 power in the denominator. Next, let's use the log of a quotient rule to expand this. we have log of 6 times x plus 5 squared minus log of x to the 4/3 power. We can further expand the first log as it is the product of two logs, so that we have log of 6 plus log of x plus 5 squared minus log of x to the 4/3 power. Finally, we can bring the exponents down, so that we have log of 6 plus 2 log of x plus 5 minus 4/3 log of x. This is our final answer. Let's try going backwards. We would like to write these three logs all as one single log. First, I will use the power rule to move the coefficients on each log into the argument as an exponent. We have log base 7 of x to the 1/4 power plus log base 7 of y to the 6th power minus log base 7 of w. The two logs that are added can be combined as one log that has an argument which is the product of the logs. We have log base 7 of x to the 1/4 power times y to the 6th power minus log base 7 of w. Now we can combine the two logs using the quotient rule, since we have the difference of logs. We have log base 7 of x to the 1/4 power times y to the 6th power divided by w, which is our final answer. Let's try one more problem, writing multiple logs together as one log. The first thing I would like to do is write the 5 on the third log as an exponent. Then we can combine the logs that are subtracted in parentheses using the quotient rule to get 3 times log base 2 of w plus 2 times log base 2 of w over x to the 5th. Then let's move the coefficients of 3 and 2 onto the exponents of the logs. We have log base 2 of w to the 3rd plus log base 2 of w over x to the 5th, all squared. Next, we can distribute the square to the w and x to the 5th in the second log to get log base 2 of w to the 3rd plus log base 2 of w squared divided by x to the 10th. We can combine the addition of the two logs into one log that has the product of the arguments, as log base 2 of w to the 3rd, w squared divided by x to the 10th. Combining the w terms, we have log base 2 of w to the 5th divided by x to the 10th, which is our final answer. Alright, my friends, that completes our video discussing expanding logarithms.